Welcome to solverfy.
In this video, we're going to go through the answer to question number 37 from chapter 9.4. So we're given this differential equation in terms of y, and we're asked to do a few different steps. So let's start with part A. So we're asked to show that this set is a fundamental solution set. Okay, so to show that, we need to show that each of the elements of the set is a solution to the differential equation. Then we also need to show that the set forms the set is linearly independent. Okay, so first to show that there are solutions, let's start with e to the t. Okay, so to show that that is a solution, let's let y equal e to the t. And then all of the derivatives of e to the t are just itself, because e to the t just differentiates to itself. So then y prime 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 minus 6y prime prime plus 11 y prime minus 6y is going to be, well, it's going to be e to the t minus 6 e to the t plus 11 e to the t minus 6 e to the t. So these are all terms of e to the t. So we've got 1 e to the t minus 6 e to the t, that's minus 5, plus 11 is plus 6 e to the t, and then minus 6 e to the t gets us to 0. So y is equal to e to the t is definitely a solution. The other elements of this set can be easily shown to be solutions in the same way. So now, to show that they're linearly independent, let's write it as C1 times the first element e to the t plus a constant C2 e to the 2t plus a constant C3 times e to the 3t let's say that that is equal to 0. And then clearly, because you can't multiply e to the t by a constant to get to an e to the 2t. Like you can't ever get from this to this. You can't get an e to the t to become an e to the 2t by multiplying it by a constant. So therefore, the only way to satisfy this equation is when C1 is equal to C2 is equal to C3 are all equal to 0. So therefore, it's a set of linearly independent functions, which are all solutions. So therefore, it's a fundamental solution set. Okay, part B. Okay, so we're asked to find the Wronskian of the solution set. So that's e to the t, e to the 2t, e to the 3t. So this is defined as the determinant of a matrix given by e to the t, e to the 2t, e to the 3t on the top row. And then the second and third rows are the first derivative and the second derivative of the top row. So the first derivative of the top row is just e to the t 2 e to the 2t 3 e to the 3t. And the derivative of that again is going to be e to the t 4 e to the 2t and 9 e to the 3t. Okay, then then working this out, expanding over the top row, it's going to be e to the t times by, then derivative of the bottom right 2 by 2 matrix is going to be 2 times 9, which is 18, minus 4 times 3, which is 12, all times e to the 2t times e to the 3t, which is e to the 5t. Then minus the top middle element, which is e to the 2t. Then multiply by 1 by 9 minus 1 by 3, which is 3, times e to the t times e to the 3t, which is e to the 4t, plus e to the 3t, which is the top right element, and the bottom left 2 by 2 matrix. The determinant of that is 1 by 4 is 4, minus 1 by 2 is 2, times by e to the t times e to the 2t, which is e to the 3t. Okay, so 18 minus 12 is 6. Then we've got 6e to the 6t, but then each of these terms is going to be in terms of e to the 6t, so we can take that out. So that's 6, and then from the middle term we've got minus 9 minus 3, so that's going to be minus 6. Then on the right we've got plus 4 minus 2, which is 2, times by e to the 6t, which is 2 e to the 6t, because 6 minus 6 is 0. Part C. Okay, so we're told to let x1 be equal to y, x2 be equal to y prime, which we can write as x1 prime, because x1 is equal to y, and x3 equal to y double prime, which we can write as x2 prime. And then since we've defined x3 as y prime prime, we can then rewrite the original differential equation as, well, it's y prime prime prime, which is x3 prime. And then we can put the other terms on the right hand side. So that's going to be 6 times y double prime, which is just x3, minus 11 times y prime, which is x2, plus 6 times y, which is just x1. Okay, so now we can write that in matrix form. So we've got a matrix, a vector x1, x2, x3, differentiated. It's going to be equal to some matrix times by the vector itself, x1, x2, x3. So we need to write these equations at the top in this form. So starting with this one, we've got x prime is equal to x2. So that's x1 prime is equal to x2. So there's no x1s, there's one x2, and there's no x3s. Next up, this one. We've got x2 prime is equal to x3. So that's on the right hand side, there's no x1s, there's no x2s, there's one x3. And finally, this guy, we've got x3 prime is equal to, well, we've got 6 x1s, we've got minus 11 x2s, we've got 6 x3s. So that's writing it in matrix form. Next up, we've got part D. So we need to verify that that this set S, which is equal to the set of vectors e to the t, e to the t, e to the t, e to the 2t, 4 e to the 2t, oops, and then that's 2 e to the 2t, 4 e to the 2t, and e to the 3t, and 3 e to the 3t, 9 e to the 3t. Just putting dots instead of having to write out all of the exponentials. Okay, to show that this is a fundamental solution set, we need to show first that each of them are solutions to the matrix equation, and then we need to show that they're all that they form a linearly independent set. Okay, so let's first show that this guy is a solution to the matrix equation. So let's let x be equal to this vector, e to the t, e to the t, e to the t. Then x prime is just going to be equal to itself because they're all e to the t's. Okay, but what about ax? Well, it's going to be a is 0, 1, 0, 0, 0, 1, 6, minus 11, 6, times by x, which can be written as, well, we could take an e to the t out the front, and then times that by the vector 1, 1, 1. So this is just going to be e to the t times 0 plus 1 plus 0 is just 1, 0 plus 0 plus 1 is 1, 6 minus 11 is minus 5, plus 6 is 1. And this is nothing but x itself, which is the same as x prime. So therefore, that is a solution of the equation x prime equals ax. And we can show the same for this guy and this guy, which I'll leave you to do. Then to show that they are linearly independent is very similar to what we did in A. We just do it for each of the components of the vectors. And finally, part E, we're asked to find the Wronskian of S. So that's just going to be the determinant of the vector given by each of the where each column is a vector from the set S. So first column is the first vector, e to the t, e to the t, e to the t. Second column is the second vector, e to the 2t, 2 e to the 2t, 4 e to the 2t. Then the third one is e to the 3t, 3 e to the 3t, 9 e to the 3t. Okay, and this is exactly the same as the, where are we? Okay, so that's exactly the same as the determinant of the matrix that we found in part B. So it's exactly the same as the Wronskian that we found in part B. which was the Wronskian of the functions e to the t, e to the 2t, and e to the 3t. And that completes our answer